The first step in development of preparative method is optimization of mobile phase gradient in order to perform separations with good resolution so that each compound is isolated as pure as possible and requires little additional workup, and within a reasonable amount of time so that solvent consumption and time or workforce consumption are minimal and a large number of samples can be processed. Initial parameters are set from experience. The injection volume is 1 microliter, and this will be optimized in subsequent steps. The mobile phase flow is 4 milliliters per minute. The volume flow is higher than for analytical methods, since the column has 2 times greater diameter, that is, 4 times greater cross-section. The mobile phase consists of 0.05% aqueous formic acid and methanol. Formic acid is added to improve peak shapes of phenolic compounds and carboxylic acids by ionization suppression. The starting methanol content is 60% and increases to 70% in 18 minutes. This will also be optimized in subsequent steps if needed. After elution, for column washing, methanol content will increase to 100% in the next 2 minutes, and it will be kept for additional 4 minutes. Post time will be 4 minutes. The elution will be monitored by UV on several wavelengths to ensure detection of all peaks. 215 nanometers will be used for universal detection. Now, our compounds, or lignans, have absorption maxima at about 280 nanometers and about 330 nanometers. However, due to high concentrations, the detector would be overloaded at these wavelengths, resulting in a flat line at high absorbance. Instead, in addition to 280 nanometers, we will use several suboptimal wavelengths such as 300, 310 and 350 nanometers. This will allow the operator to estimate the elution profile of compounds with different concentrations and collect the fractions accordingly. After instrument equilibration, a very small amount of the sample, for example 0.2 microliters of 500 milligrams per milliliter solution, that is about 100 micrograms, is injected. If only a small amount is available, for example less than 1 milligram, the entire effluent can be collected, evaporated, and reused, which is labor intensive but sometimes necessary. In our case, we can afford to spend about 100 micrograms. The run is completed, and now we can load our data file. We show the total wavelength chromatogram, and we can see that the separation is generally satisfactory, although the major peaks overlap. If needed, we could try to improve the separation by varying the gradient and rerunning the sample, or if the satisfactory separation cannot be obtained, it is necessary to change the selectivity, which could be done either by changing the chemistry of mobile phase or by changing the stationary phase. Now we need to optimize the injection volume. For that purpose, increasingly larger sample volumes will be injected from 0.5 to 6 microliters. The sample concentration is again about 500 milligrams per milliliter. Now we can see the results. So this is from 0.2 to 6 microliters. As we can see, if we inject low volumes, such as 0.2 microliters of sample, we will obtain good peak shapes and adequate separation, comparable to analytical HPLC, but at the expense of needing to perform hundreds of separations, which is not practical. It is labor intensive, blocks the instrument for a long time, and generates large volumes of chemical waste. On the other hand, high injection volumes lead to column overload, resulting in poor peak shapes and poor separation of closely eluting peaks. Additionally, if the sample is dissolved in a strong solvent, in our case it is in acetone, high volumes will result in partial premature elution, peak deformation, or even peak splitting and poor separation. In this case, we choose a compromise volume of 6 microliters, which corresponds to about 3 milligrams. So we will inject in overload mode, which is a common practice in preparative chromatography, especially in early stages. And with total amount of 54 milligrams of sample, it will take us about 20 to 30 runs. We can now define the fractions. Since all the peaks will be interesting for us, we will perform collection throughout the entire run, except for dead volume and washing step. So this will be the fraction 1, this interval the fraction 2, this interval fraction 3, these two colluting peaks fraction 4, these peaks fractions 5a and 5b, and so on. If the peak overlapping occurs, such as this case, we can try collecting the leading, the middle, and the trailing part of the overlapped peak as separate fractions. Then the leading and trailing part will be almost pure, while the middle part will require an additional cycle of separation, but now with lower column loads. In our case, we will just separate the leading and trailing part and then purify each one. Now we can finally perform the preparative separation. The 6 milliliters of sample will be injected, and the operator will closely monitor the DAD signals and compare them to the previously defined collection schedule. Each fraction will be collected into a pre-labeled test tube or a flask with the needed vessel volume calculated according to the fraction duration and volume flow. After a single run is completed, the fractions are transferred into pre-labeled large volume vessels, and the next aliquot is fractionated into the same collection vessels. This way, if something happens to the fractions from one run, for example accidental spilling or fractions merging, the bulk will still be safe. Now, our compounds need to be isolated from the collected fractions. While this could be done by evaporation, in this specific case, high water content would make the process extremely slow, and the presence of acid would catalyze lactone ring opening or alcohol group dehydratation. Instead, only methanol is removed by evaporation, and then lignans are extracted from aqueous phase by liquid-liquid extraction with chloroform, and then the chloroform extract is dried and evaporated to obtain the pure compounds.